Right now, at the very top of the world and the very bottom of the world, two giant sheets of ice are breaking apart in ways that scientists did not expect and did not predict. And honestly, it is scary how fast it is happening. In the Arctic, winter sea ice just tied one of the lowest levels ever measured since satellites first started watching Earth in 1979. That is almost 50 years of data, and this year is one of the worst 2 years on record. At the same time, way down at the South Pole, Antarctica, a place that spent decades looking almost untouchable by global warming, has suddenly flipped into a downward spiral. Scientists are calling it a genuine surprise. Not a small surprise, a real one. The kind that makes researchers go back and double-check their own equipment because they cannot believe what the numbers are telling them. Here's the strangest part of all of this. These two places are breaking down for almost completely different reasons, at the exact same time, on opposite ends of the same planet. One is an ocean covered in floating ice. The other is a continent buried under ice that is thousands of feet thick in some places. Two totally different systems, doing something scientists have never seen before, at the same moment in history. So what is actually going on? Why did decades of seeming calm suddenly break apart in just the last couple of years? And what does any of this mean for people who live nowhere near an iceberg or a penguin? Stick around, because by the end of this video, you are going to understand exactly what is happening at the top and the bottom of the world, in simple terms, without a bunch of confusing science jargon. You will hear why scientists who have studied this their whole careers are using words like unprecedented, and you will learn what this could mean for weather where you live, even if you are thousands of miles away from either pole. Before we go further, if you have ever wondered whether all these melting ice headlines are exaggerated or if they are actually true and serious, this video lays out the real data, calmly, so you can decide for yourself. It takes a lot of time and research to pull all of this together in one place, so if you find this helpful, hitting like and subscribing really helps this channel keep making videos like this one. Now let us start at the top of the world, because the Arctic story has the longest paper trail, and it sets up everything else you're about to hear. For years, something strange was happening in the data up north, and almost nobody outside of science circles noticed it. Arctic winter sea ice is the thick layer of ice that spreads across the top of our planet every year, usually between October and March. For decades, as the planet warmed up, this ice had been shrinking year after year. But then, around 2005, something odd happened. The shrinking seemed to slow down and almost stop. Year after year, the amount of ice at its winter peak stayed low compared to the 1980s, but it was not dropping any further. It looked like the ice had found a new level and was just staying there. Scientists who studied the numbers even started calling this a pause, like the ice loss had paused or gone into a kind of holding pattern. Some scientists wrote papers about it. They said the winter ice was no longer sliding downward the way it used to. This idea stuck around for almost 20 years. People believed it. Then 2025 happened, and that entire idea fell apart overnight. Between the winter of 2024 and the winter of 2025, Arctic sea ice, right during the time of year when it is supposed to be growing the thickest, dropped by almost 6% in a single year. Let that sink in for a second. 6% in one single year. To understand how big that is, you need to picture the size of area we are talking about. Arctic winter sea ice normally covers about 14 million square kilometers. 6% of that is an area of ice that vanished, roughly twice the size of the entire state of Texas. Gone in 12 months. And here's the detail that really shook scientists to their core. This drop happened at the exact time of year when Arctic ice is supposed to be at its strongest. Winter in the Arctic means months of total darkness, and that darkness usually builds up the thickest ice of the whole year. Instead, the ice was sitting at levels nobody had seen in almost 50 years of measuring at the exact moment it was supposed to be piling up the most. Scientists at the University of Southampton, working with the National Oceanography Center in the United Kingdom, could not just accept this number without checking it first. So they built computer simulations to test whether a drop that steep was even possible, given everything we know about how fast the Arctic has been warming. They ran the numbers over and over, comparing them to decades of old climate data, hunting for any similar event that had ever happened before under similar warming conditions. What they found were events that were rare, but they were not impossible. They had happened before, just not very often. And here is something the researchers did not expect going into this study. The very next winter, in 2026, ice cover actually ticked up a little bit from the record low the year before. Just a small bounce back. And when the scientists ran their simulations again, the models predicted that same small bounce, almost exactly. Now, that might sound like good news. Ice crashing and then bouncing back a little bit sounds like the system is trying to heal itself. But the scientists were very clear about what this small recovery actually meant, and it is not what you might hope. In every similar case, their models produced from history, once ice dropped that steeply, it almost never fully bounced back to where it used to be. Instead, the whole system settles into a new, lower level, and it wobbles around that new lower level for years afterward. In other words, that small recovery in 2026 was not the beginning of things going back to normal. It was Arctic ice finding a new, much lower normal to bounce around inside of, and that difference matters a lot. It is worth pausing here for a second because this directly disproves the idea that had built up around that so-called pause everyone believed in for 20 years. For a long time, people used that pause, sometimes honestly and sometimes not so honestly, to argue that Arctic ice loss was slowing down and that all the warnings about melting polar ice were overblown. This new research proves the opposite, using hard numbers. That pause was never a real stabilization. It was just a temporary quiet period sitting on top of a much longer ongoing decline. And the moment conditions lined up the wrong way in 2025, the decline picked up exactly where the old trend had left off. Except instead of happening slowly over many years, it all happened in one violent year. NASA and the National Snow and Ice Data Center at the University of Colorado Boulder looked at this completely separately, using their own data, and they confirmed the exact same pattern. Arctic sea ice hit its highest point for the year on March 15, 2026, reaching just over 14.29 million square kilometers. That is basically tied with the 2025 peak of 14.31 million square kilometers. 2 years in a row now, the Arctic has posted its lowest winter peak ever measured since satellites started watching in 1979. Scientists at NSIDC and NASA said these 2 years were basically impossible to tell apart from each other, both sitting at the very bottom of a 47-year record. Jennifer Francis, a senior scientist at the Woodwell Climate Research Center, compared this pattern to a warning sign you might see at a doctor's checkup. It is the kind of symptom that by itself might not mean disaster is coming right away. But when it keeps showing up test after test and it keeps pointing in the same direction, doctors do not wait around for a full-blown crisis before they start treating the problem. Climate scientists are making that exact same argument about the Arctic Ocean right now, so why does winter ice even matter this much? Most people picture the Arctic crisis as a summer story, with pictures of shrinking September ice and polar bears stranded on tiny ice chunks. But winter ice does something that summer ice simply cannot do. It acts like a lid. It is the barrier that separates a relatively warm ocean, sitting just below freezing, from the air above it, which can be 60 or 70 degrees colder during the darkest months of the year. When that lid is thick and solid, heat and moisture stay trapped in the ocean where they belong. But when that lid gets thin, or develops gaps and cracks, heat escapes up into the atmosphere all winter long. And that extra heat does not just stay hovering over the North Pole and mind its own business. It spreads out. It shifts pressure patterns across the whole hemisphere. It feeds into something called the jet stream, which is basically a river of fast-moving air high above us that steers a lot of our weather. Scientists have increasingly linked a weaker Arctic ice lid to the kind of extreme cold snaps and messed up storm patterns that show up thousands of miles south in places like the American Midwest or Northern Europe in the middle of winter. So a thinner Arctic winter ice cap is not just some faraway statistic that only matters to polar bears. It is a lever, and when that lever gets pulled, it can reach all the way down into the weather systems that the rest of us live under every single day. The mechanism behind all of this comes down to something called albedo. And once you understand this one idea, you will never look at a picture of polar ice the same way again. Ice and snow are bright. They reflect most of the sunlight that hits them straight back out into space, like a mirror. Open ocean water, on the other hand, is dark, and dark surfaces do the opposite of mirrors. They absorb sunlight instead of bouncing it away. So here's what happens. When a patch of sea ice disappears and gets replaced by open water, that patch of ocean stops reflecting sunlight and starts soaking it up instead, which warms up the water underneath it. That warmer water then makes it even harder for new ice to form the following winter, which exposes even more dark ocean the year after that, which then absorbs even more heat than before. It becomes a loop, a feedback loop. It is literally the planet's own natural thermostat, except running backward, making things worse instead of keeping them balanced. This loop is actually one of the biggest reasons the Arctic right now is warming almost 4 times faster than the rest of the planet, on average. Every single square kilometer of ice that disappears is not just a sign that warming is happening. It actually becomes a cause of even more warming after it. That is exactly why scientists watching these numbers describe the ice decline as something that can speed itself up, rather than just leveling off on its own like a plateau. Now let us fly all the way to the complete opposite end of the Earth. Because while all of this has been happening up in the Arctic, Antarctica has been living through its own completely separate story. And for most of the last several decades, that story looked like the exact opposite of what was happening up north. This next part genuinely confused climate scientists for years, and it is worth explaining carefully, because the contrast between the two poles is really the key to understanding why what is happening right now feels so alarming to the people who study this for a living. Unlike the Arctic, which is basically an ocean surrounded by land, Antarctica is a continent surrounded by ocean. The difference in geography matters enormously, more than you might think at first. For decades, sea ice around Antarctica simply did not follow the same warming pattern as the rest of the planet. While Arctic ice was steadily shrinking year after year after year, Antarctic sea ice was holding roughly steady. In some years, it was actually growing slightly. Climate scientists spent years trying to explain this using a mix of different reasons. Stronger winds circling the continent, cold meltwater running off the ice sheet, which created a protective layer of colder, fresher water sitting on the ocean surface, and the simple fact that sea ice surrounding a whole continent behaves very differently than sea ice floating inside a partly enclosed ocean up north. For a long stretch of time, Antarctica seemed protected, almost immune, from the rapid ice loss happening up in the north. Then, in 2016, that protection broke. Antarctic sea ice, which had been slowly climbing or holding flat for almost 4 decades, suddenly reversed course, almost overnight, and started falling sharply again and again. It hit a record low in 2022. Then it broke that same record again in 2023, dropping to a level so far below the historical average that the missing ice alone covered an area larger than the entire country-sized landmass of Greenland. That left researchers with a very uncomfortable question to answer. What actually changed in 2016 that flipped one of the most stable ice systems on the entire planet into one of the most unstable? A team of researchers, once again working out of the University of Southampton, published findings this year describing what they are calling a triple whammy. That means 3 separate problems piling on top of each other at the same time, all working together to drive Antarctic sea ice into what they are calling a downward spiral. The first problem is a warming layer on the surface of the ocean, which has worn away the cold, fresh water buffer that used to protect the ice from underneath. The second problem is a shift in wind and pressure patterns circling the Southern Ocean, patterns connected to something called the Southern Annular Mode. This pattern has been sitting in what is called a persistently positive phase, which basically means lower air pressure sitting over the Southern Ocean near Antarctica, and higher pressure being pushed further north into the middle latitudes of the globe. That setup strengthens the powerful westerly winds that circle the entire continent, and it has been closely tied to unusually warm, wet conditions, specifically around the Antarctic Peninsula, which happens to be one of the fastest warming places on the entire planet. The third problem involves changes happening deep in the ocean itself. Shifts in ocean currents are pulling warmer water up from far below, bringing it into direct contact with the bottom of the ice, melting it from a direction that used to stay fairly stable and predictable. On their own, each of these 3 problems might have been survivable. The ice system could probably have handled just one of them. But together, compounding on each other year after year, they have pushed the whole system into a state that researchers describe as actively reinforcing its own decline, instead of naturally correcting itself the way it used to. As of the most recent monitoring reports, Antarctic sea ice extent is sitting at the 6th lowest level ever recorded for this particular point in the season. And the regional data paints a very divided picture around different parts of the continent. Along the Atlantic side of the Southern Ocean, and in the smaller seas near the Antarctic Peninsula, ice has been retreating extremely fast. Meanwhile, other sections closer to the Ross Sea have stayed much closer to their historical averages, cooled partly by unusually strong southerly winds pouring off an intensified low-pressure system known as the Amundsen Sea Low. That very same pressure system has been simultaneously pushing warm northerly air into the Bellingshausen Sea on its eastern side. That explains why, if you looked at a map of Antarctica right now, you would see one region running much colder than normal sitting directly next to another region running much warmer than normal, both of them being driven by the exact same spinning weather system nearby. This kind of regional patchwork might sound like a small technical detail, but it actually connects directly to one of the most shocking individual events to come out of Antarctica in recent memory. Something that, on its own, would have been the single biggest polar story of the entire year in any other context. In the middle of the Antarctic winter of 2024, during the months when parts of the continent sit in near total darkness and temperatures usually stay well below negative 30 degrees Celsius, East Antarctica experienced a heat wave that broke every model scientists had built to describe extreme events on that continent. Temperatures in parts of East Antarctica spiked by as much as 28 degrees Celsius above the normal seasonal average, and they stayed elevated for more than 2 weeks straight. Scientists studying this event tried to put that number into a context that would actually make sense to people who have never set foot near a polar research station. The comparison they landed on is almost impossible to picture in your head. An anomaly of that scale happening in the United Kingdom in the middle of January would push temperatures there into the mid-30s Celsius, basically transplanting an entire summer heat wave into the dead of a British winter. That is the scale of what happened in East Antarctica, except it happened during a season when the sun barely rises above the horizon at all. Researchers who studied this event afterward and published their findings this year in a peer-reviewed climate science journal concluded that this was not just some random fluke of weather. It was driven by a combination of three things working together. A weakened polar vortex, which is the ring of cold air that normally seals off the interior of Antarctica and keeps warm air out. An atmospheric river, which carried an unusual surge of warm, moist air deep into the continent's interior. And record low sea ice conditions offshore, which removed one of the natural barriers that would normally block that warm air from traveling so far inland. Climate modeling done by the very same research team showed that human-caused warming significantly increased both how intense and how long this event lasted, making an anomaly of that size far more likely than it would have been before the industrial age began. And here is the detail that should genuinely worry anyone paying close attention. The researchers were very clear that this heat wave was not a one-time fluke. They described it as a preview, a small glimpse of the kind of extreme event that is likely to happen more and more often as the underlying warming trend keeps building over the coming decades. If a sudden winter heat wave sounds a little abstract or hard to picture, the story of a single glacier makes the real consequences much easier to understand. Hectoria Glacier, sitting along the Antarctic Peninsula, recently became the fastest retreating glacier ever documented in the modern satellite record. Over a period measured in just months, not years, the glacier's grounding line, which is the point where the ice stops resting on solid rock and starts floating on the ocean instead, retreated roughly 8 kilometers. And nearly half of that entire collapse happened in an extraordinarily short window of time. Scientists studying this trace the cause back to the shape of the ground underneath the ice itself. Most glaciers sit on bedrock that slopes upward toward the coast, which naturally slows a retreating glacier down the further back it retreats, kind of like a ramp that gets harder to slide down the higher up you go. But Hectoria sits on an unusually flat stretch of seabed that lies below sea level. Once the glacier lost contact with that flat bed, there was almost nothing left to physically stop the collapse. Huge slabs of grounded ice broke away one after another in quick succession, instead of the slow, gradual retreat that scientists are used to seeing and modeling. Researchers have flagged this as a genuinely important discovery, not just because of how fast Hectoria itself collapsed, but because it reveals a mechanism that could apply to other glaciers sitting on similarly flat, below sea level bedrock across West Antarctica. Several of those glaciers hold enough ice to meaningfully raise sea levels around the entire globe if they end up behaving the same way Hectoria did. This is a good place to step back and ask the obvious question that anyone hearing all of this for the first time should probably be asking. Is the planet more unstable right now than it has ever been before? Or are we simply watching normal, if severe, consequences of a warming trend that has been building for over a century, just playing out in two very different physical systems at the same time? The honest, evidence-based answer sits somewhere in between those two ideas, and it is worth being precise about it, rather than reaching for whatever framing sounds the most dramatic. The Arctic and the Antarctic are not directly talking to each other in any physical sense. There is no single mechanism linking a collapse at the North Pole directly to a collapse at the South Pole happening in real time. They are separated by an entire planet, different ocean basins, different patterns of air circulation, completely different physical geography. One is an ocean rimmed by land, the other is a continent surrounded by ocean. What connects the two poles is not some direct physical link between them. It is the same underlying driver behind both stories, which is a planet steadily building up more and more heat because of rising greenhouse gas levels, and that heat is expressing itself through whatever regional weak spot happens to be most vulnerable in each location. In the Arctic, that weak spot is the albedo feedback loop acting on floating sea ice sitting in a warming ocean. In Antarctica, it is a more complicated mix of shifting winds, an eroding cold water buffer layer, and deep ocean circulation changes, all acting on a continent that had, until recently, been unusually resistant to the same warming showing up literally everywhere else on Earth. It is also worth directly addressing something that comes up constantly whenever ice and climate trends get talked about publicly, because skipping past it would leave a gap in this whole picture. There have been individual studies over the years, and individual years within longer records, that showed brief periods of ice recovery at one pole or the other. And those individual data points sometimes get pulled out of context by people to argue that the entire warming story is overstated, or that predictions made decades ago never came true. To be fair, some of those old predictions genuinely did miss their timelines pretty badly, and it is fair to point that out honestly. But a short-term prediction missing its date is a completely different thing from a multi-decade physical trend that has been measured continuously by satellites. And the research described in this video is not built on speculation or a single scary headline. It is built on nearly 50 years of continuous, independently verified satellite measurements, cross-checked by multiple national space and ocean research agencies across different countries, and it consistently shows the exact same long-term direction, even when individual years wobble the other way for a little while. A single cold winter or 1 year of partial recovery does not undo a 5-decade-long trend, in exactly the same way that one unusually mild afternoon in the middle of summer does not undo the changing of the seasons. So what does all of this actually mean for people living nowhere near either pole? This is where these two stories connect back to daily life in ways that are really easy to overlook if you are not paying attention. Sea ice loss at the poles does not directly raise sea levels in a major way on its own, because floating ice, kind of like an ice cube already sitting in a glass of water, has already displaced its own volume of water before it even starts melting. The real sea level danger comes from land-based ice, like glaciers and ice sheets that sit on solid rock, the same way Hectoria Glacier does. Every meaningful acceleration in the collapse of those kinds of glaciers translates directly into rising coastlines everywhere on Earth, not just near Antarctica. But sea ice loss still matters enormously because it is one of the primary triggers that speeds up everything else. Less sea ice means more open, dark oceans soaking up heat. More heat in the ocean, and the atmosphere destabilizes the very glaciers sitting on land nearby, the same glaciers that do directly raise sea levels when they collapse. Less Arctic winter ice reshapes pressure systems that influence storm tracks and cold outbreaks across the entire northern hemisphere. And a weakened polar vortex over Antarctica, the same mechanism blamed for that extraordinary 2024 winter heatwave, has documented links to disrupted weather patterns that reach all the way up into the middle latitudes of the southern hemisphere. There is one more concept worth understanding here, because researchers who track this closely have started using a specific term for a scenario they are watching for at both poles at the same time, something called a blue ocean event. This term refers to the moment when sea ice extent in a given region falls below roughly 1 million square kilometers, which is a threshold low enough that satellite images of that ocean area would show overwhelmingly open, ice-free blue water, instead of the white expanse people normally picture when they think of the polar regions. Researchers tracking current trends have raised the possibility that both an Arctic blue ocean event and an Antarctic blue ocean event could theoretically happen within a similar window of time in the coming years, something that has never happened at the same time in the entire satellite era. It is important to be precise about what this term does and does not mean. It does not mean that all the ice on Earth suddenly vanishes. It refers specifically to the seasonal minimum ice extent in certain ocean basins dropping below that defined threshold. It is a regional and seasonal event, not some kind of permanent planet-wide loss of all polar ice everywhere. But even a temporary blue ocean event at either pole would represent a level of open, sunlight-absorbing ocean water that our current climate system has essentially never experienced during the entire period we have been able to measure it with satellites. And remember that albedo feedback loop we talked about earlier? It means that even a temporary event like this could leave a lasting mark on how quickly the surrounding ice is able to recover in the years that follow. Now let us be fair to the counterpoint that always gets raised whenever stories like this circulate online, because a good explanation should address it honestly instead of just waving it away. Antarctica's behavior before 2016 genuinely did puzzle climate scientists for a long time. And for years, that puzzle got used, sometimes fairly and sometimes in bad faith, to suggest that the whole warming picture was less certain than advertised. But the explanation for that early stability was never that warming was not happening at all. It was that Antarctica's specific geography and ocean circulation were, for a period of time, actively working against the warming signal that was already showing up in the sea ice, buffering it through mechanisms like cold meltwater layers and strong circumpolar winds. Once those buffering mechanisms started breaking down around 2016, which is exactly what the triple whammy research describes, Antarctica stopped being the exception to the rule and started catching up to the trend that had already been running in the Arctic and almost everywhere else on the planet for decades. The pause was real. It just was not permanent. And understanding why it ended is far more scientifically interesting than either dismissing it completely or treating it as proof that the whole system was broken all along. If you zoom out far enough, both of these stories are ultimately about the exact same underlying physical reality, just expressing itself through two very different regional systems. And this is really the piece worth remembering above everything else in this entire video. Ice systems that appear stable for years, or even for decades, are not automatically evidence that a warming signal has stopped happening. Sometimes they are evidence that a region simply has protective mechanisms holding the line temporarily. Mechanisms that can and do break down once the underlying pressure builds up past a certain point. Whether that pressure builds up gradually and then reveals itself all at once, the way it did in the Arctic's 2025 crash, or whether it quietly accumulates for years before flipping an entire continent's ice trend in a single season, the way it did in Antarctica after 2016. Scientists monitoring both poles right now are watching several specific things going forward, and these are the indicators worth keeping an eye on if you actually want to understand where this heads next, rather than just reacting to whatever the next dramatic headline happens to say. In the Arctic, researchers will be watching to see whether winter sea ice settles into that lower band the recent modeling predicted, fluctuating without ever fully recovering, or whether it somehow finds a way to stabilize at a level closer to what was considered normal even just a decade ago. In Antarctica, the key indicators are whether the triple whammy mechanisms driving the current decline keep reinforcing each other, or whether natural variability in the Southern Annular Mode and the Amundsen sea low shifts back toward a configuration that gives the ice a real chance to rebuild itself. And across both poles, scientists are watching closely for one specific combination of conditions: low sea ice, a weakened polar vortex, and an unusually active atmospheric river, the exact same combination that produced the astonishing 2024 East Antarctic heatwave. Because if that same combination shows up again, researchers have already told us what to expect from it. None of this requires you to live near a coastline or near a research station for it to matter to you directly. Weather patterns, shaped by a warming Arctic and a warming Antarctic, reach into ordinary life everywhere, through disrupted storm tracks, shifting growing seasons for crops and food, and the kind of unusual cold snaps or heat waves that used to be described as freak, random events, and are now increasingly described by scientists as part of an expected, predictable pattern. Understanding the actual mechanisms behind these headlines, rather than just reacting to the scary numbers attached to them, is really what separates genuine awareness from simple anxiety. And that distinction matters a lot, because awareness without understanding tends to either curdle into panic or get dismissed entirely the moment a single data point runs the other direction for just one season. The honest takeaway from everything researchers have published this year is not that the poles are collapsing overnight in some sudden, single, planet-ending event. It is that two enormous, complex physical systems, each with its own decades of relative stability behind it, have both entered periods of measurable, well-documented, and mechanistically understood decline at the same time, for reasons specific to each region, but tied back to the exact same root cause underneath it all. That is not a prediction dressed up as certainty. It is what nearly 50 years of consistent satellite measurement, cross-checked by independent research teams across multiple countries, is currently showing us in the raw data itself. It also helps to put the instruments themselves into context, because the confidence behind everything described in this video rests entirely on the quality of what is actually measuring these changes in the first place. The Arctic and Antarctic numbers referenced throughout this video come from microwave radiometer instruments carried on multiple satellites, including sensors operated jointly by Japan's National Institute of Polar Research and the Japan Aerospace Exploration Agency, alongside NASA and the National Snow and Ice Data Center in the United States. These instruments do not rely on visible light, which means they can measure ice extent continuously, straight through the total darkness of polar winter, and straight through heavy cloud cover too. Conditions that would make traditional photography completely useless for months at a time. That continuous all-weather coverage is exactly why the record stretching back to 1979 is considered so reliable, and it is why a 6% single-year drop in the Arctic, or a sixth lowest ranking in Antarctica, are not treated as noisy, uncertain guesses. They are treated as precise, cross-verified figures that multiple independent institutions in multiple countries arrived at separately and then confirmed against each other afterward. When several unrelated research groups, working with different satellites and different processing methods, all land on the same number, that is about as strong as observational science gets outside of a controlled laboratory setting. It is also worth remembering that this satellite record, as long as it might feel, only stretches back 47 years, which is really just a blink of an eye in geological terms. That means every single record broken in 2022, 2023, 2025, and 2026 is not just a record within living memory. It is the lowest point ever documented by direct instrumentation, full stop, with no equivalent baseline from before the satellite era to compare it against. And that is exactly why researchers keep reaching for words like unprecedented rather than simply calling it unusual. What happens next depends on decades of decisions still being made right now, the same way it always has with climate trends that build slowly and then arrive all at once. Scientists will keep flying over these regions, keep dropping instruments into the ice, and keep publishing whatever the data actually says, whether that turns out to be more reassuring or more alarming than what we already know today. If you want to keep up with how both of these stories develop, whether the Arctic settles into a new lower baseline or the Antarctic triple whammy keeps compounding on itself, subscribing is the easiest way to make sure you catch the next update the moment new research comes out. And sharing this video with someone who still thinks both poles are simply recovering on their own is one of the more useful things you could do with the next 30 seconds of your day. Let me know in the comments which of these two stories surprised you more. Was it the Arctic's sudden crash after 2 decades of apparent calm? Or was it Antarctica's slow-motion reversal after decades of looking like the one part of the planet that might actually hold steady forever? Either way, both ends of this planet just proved something important, that stability and permanence are two very different things. And the ice-keeping track of that difference does not particularly care whether we were watching closely enough to notice in time.